University, Visakhapatnam. After his PhD, he served as NOAA Trust at City College of New York, USA, Maldives. Maldives Climate Observatory, Hanimado, Leibniz Institute for Tropospheric Research, Germany, IIT Bombay, and Goa University during 2009 to 2017, and joined National Atmospheric Research Laboratory, Gadanki, India as scientist in 2017. Dr. Madhavan is presently working as scientist in aerosol radiation and trace gases ARTG group at. His research interests include atmospheric aerosol and clouds observation and radiative transfer modeling, remote sensing techniques, aerosol cloud interaction studies, development of aerosol and cloud retrieval algorithms, multivariate factor analytic techniques, example, principal component analysis and positive matrix factorization and 3D cloud radiation effects. He has published more than 40 papers in international peer-reviewed journals in the field of atmospheric aerosols. He has served as reviewer and guest editor for several international reputed high-impact journals. He is a member of several national and international scientific bodies. Now I now request Dr. D.L. Madhavan to give his valuable talk.
Hello, am I audible? Hello?
You are audible to us.
Yes, you are audible.
You can see my screen also?
Yes.
Okay, thank you. Yeah, thanks for the introduction. And firstly, I thank the organizers for giving me an opportunity to deliver the talk. And my talk is on atmospheric pollution Lidar. And this work was actually a part of the work that I have conducted during one of my postdoctoral research during 2012 at IIT Bombay. And it is part of an Indo-French project in which there are people from India and also people involved from France, and it's an industrial sponsored project. So is my slides moving? Yes, okay. So I first like to acknowledge the Indo-French project team in which I was working with at IIT Bombay at that time, and the other partners are from France, and there's an industry that is also involved who developed the Lidar as part of this project. And our focus of the work was mainly on understanding the capability of this Lidar to ascertain the particulate mass concentration from the Lidar signal. So in this context, we were trying to understand different methods, and now I will be presenting on that aspect. So the background of this work is actually on, we know that urban areas are increasing day by day, and the scenario of air quality is of utmost importance in terms of the climate and also adverse health effects. And there are popular ways of measuring the particulate mass concentration, which includes conventional sampler based methods and also in situ particle counter based methods. But however, it is like these are point based measurements where we cannot able to understand how the spatial variability of this particulate mass is changing in a particular near to a vicinity of a source, or to understand real time or dynamic mapping. There are some of the issues that we have. In one of the aspects is large diversity in the sources, and aerosol types are very diverse, and different production and removal mechanisms exist, and heterogeneous concentrations and properties in space and time. Real-time estimation of PM at high temporal and spatial resolutions will be always useful to understand the exposure of particles and human health effects. So going further, based on the previous points that I mentioned and the complexities that are involved, so we find that Lidar remote sensing is one of the useful technique and is very sensitive to aerosols because of its capability for large range of investigation and high repetition rate. So in this context, the elastic backscattering Lidar of compact size plays a vital role, And we normally focus on how to develop the method to convert this lidar signal to particulate mass, so especially in the vicinity of intense source. So intense sources are like the emission source and the measurement point will be less than 1 kilometer range. So these emission sources can be of any type. So maybe there might be biomass, fuel burning, or any chimney based things, or any industrial locations where there is sources of emissions. So in this slide, you can see that the Leosphere EZ lidar, which was developed by them, and this is a UV lidar that uses uh, 355 Nd:YAG 355 nanometer laser source with 16 millijoules and a pulse repetition of 7 nanoseconds. And it has both, it has a spatial resolution of around 1.5 meter to 15 meters, and also temporal resolution can be set to from 1 second to 30 seconds also. So we use this EZ lidar because of its capabilities, like it is compact, like it can be easily carried in a car, and also it is very, its overlap region is almost very low, like less than 200 meters or so, and it's transportable, and it is eye safe and invisible visible, and you can have automatic observations, and it has very high sensitivity, around 50 nanometer to aerosols, and high resolution. So keeping in view of all these capabilities, and also the possibilities of different modes of operation. So as you see here, this is a vertical scanning modes that were observed in an urban location in France. And you see in summer and winter, the altitudinal variation of the aerosol extinction coefficient in summer and winter are two contrasting things you can see. And then the other mode of operation is horizontal scanning. So horizontal scanning is like at a fixed altitude, we try to scan around in a horizontal mode, and from we can see how in a spatially the emission sources are distributed or dispersed during a particular time. So this picture actually shows, there is an echo coming. Yeah. So this picture actually shows the way the measurements were done, along with co-located other OPC measurements, nephrometer, filter-based, and ethylometer-based measurements. So I will come to this point in the later slides, what we were making the observations and what we found. So before we start, the basic thing is the lidar equation. So we all know this, we were hearing from yesterday onwards the lidar equation and everything. So it has mainly two experimentally controlled factors. One is system constant that actually summarizes the performance of the lidar system, and another one is range dependent measurement, which mainly speaks about the overlap function of the laser beam with a field of view and R square dependence. So there are two unknown factors now. So in this backscattering coefficient at a distance, which is determined by the strength of the lidar signal, and transmission term, which determines how much light gets lost on the way from the lidar to scattering volume and back. So it's a two-way transmission path. So that's why factor 2 is there. So in this, if you see, if we subdivide this backscattering coefficient and also the extinction coefficient denoted by alpha, so we have four components again. So within this, like we can say that four unknown aspects are there. But yesterday when we have listened to Jayraman sir's talk, he was mentioning about the lidar ratio. So lidar ratio is nothing but it's a ratio of extinction to backscatter ratio. So the molecular lidar ratio is normally determined as around, it will be equivalent to around 8 pi by 3 steradian. So with that, we try to reduce the unknowns to only 2. So now we need another like aerosol based lidar ratio. So that is one which normally we assume, or we assume at the initial stage. And then there are different methods for this, how to solve to get the aerosol extinction. Maybe you might be hearing about those methods in the next follow-up talk by Dr. Harish Gadanki. So in this lidar inversion, since our lidar is mostly focused on a horizontal scanning mode, so we normally take this range normalized signal variable as S of R, so which is log of P of R by R square. And then we consider this S naught at a reference range R naught, and this we write it and in the differential form in the below equations. And normally, whenever we assume most of the times in a horizontal mode, the scatters are homogeneously distributed. Unless otherwise, if there's no much sources, most sources are not much variable in the spatially. So the slope method inversion is actually used, but there is a complexity, like if there are no emission sources of in between, say like a plume or so, emission plume, then this method can be always be applicable until unless the horizontally it is homogeneous. But even the CLET method that can be applied in a vertical to retrieve the vertical distribution of the aerosols also is not applicable in the case of this non-homogeneous conditions during a horizontal scanning mode because of various limitations. But in this, we find that normally slope method of inversion is usually an applicable method when we are making a horizontal scanning observations. And you can see here that normally the lidar ratio is determined as extinction to backscatter ratio, which is of the is usually like it's just a ratio, but we can always take a priori relationship between them as having some beta equal to b alpha power n, and n is some specified constant which can be like varying this. So when we use this type of form for this extinction to backscatter ratio, so we can get a general solution of aerosol extinction in this form. And the limitations with this are like multiple scattering is ignored, and extinction to backscatter ratio is like again assumed, and it is unstable with respect to the alpha. Again, angstrom alpha is aerosol extinction coefficient, and we use reference point at the predetermined end range. So the solution is generated for R less than Rm instead of R greater than R naught. So Rm is our reference altitude is predetermined. Like we assume an altitude a range that is predetermined. So based on that, our retrieval also will have influence. So the lidar signal to particulate mass concentration. So aerosol mass extinction cross section, it relates this mass of the aerosol particles to optical extinction. So when we have aerosol extinction measurements and particulate mass concentrations at a particular level, then if we make a scatter plot, then the slope determined by that is actually denoted as mass extinction cross section. And this mass extinction cross section depends on various factors because it cannot be directly be determined. It's an unknown, and depends on refractive index, size, shape, and also coating. That is nothing but type of the aerosol properties. So most of the times, whenever people convert this extinction coefficient to this particulate mass concentrations, they assume these values. So these values at different locations are already provided in different literature that is available. And an important aspect of this mass extinction cross section is that it depends on ambient relative humidity. So there are also some parameterizations that exist for urban aerosols. So one can always use these parameterizations to determine the mass extinction cross section at a particular reference, at a particular relative humidity. And the variability of this mass extinction cross section need to be assessed, and the error associated with its parameterization needs to be quantified and clearly understood. So the important factor that plays an important and that plays a vital role while determining the while converting this lidar extinction coefficient to particulate mass concentration is actually this mass extinction cross section. So this is not easy to estimate from first principles. So usage of multivariate techniques can be a better possibility to account for the effect of these various factors. So this is a typical experimental setup with different instruments. So lidar is positioned at a particular altitude and pointing towards the source, emission source at the same altitude level. So you can see here in the below figure clearly that it is pointing towards a source where the emission plumes are being emitted. And there are also co-located measurements close to the source with nephelometer, ethylometer, and particle counters, which also provide some co-located particulate mass concentrations, black carbon mass concentrations, and scattering coefficients, and absorption coefficients, etc. So these are the different data sets that we get normally. And from the lidar, we obtain the extinction coefficient at 355 nanometers. From ethylometer, we get DC mass concentrations and absorption coefficients. And nephelometer, we have again scattering coefficient and scattering angstrom exponents. And OPC or GRIM provides PM1, PM2.5, and PM10 concentrations, and also the ratios of PM2.5 to PM10 and PM1 to PM2.5. And TEOM provides the mass concentration, and meteorological parameters are also measured together. So a comparison result of the lidar derived extinction coefficient versus the nephelometer scattering coefficient at the same wavelengths, you can see on the left side, indicates that scattering has dominated the extinction. And on the right side, when we see here the PM2.5 concentration measurement from the green versus the lidar derived PM2.5 corrected with RH, it provided also a good correlation among them, indicating that a linear relation exists between PM2.5 and the derived green, and that from the green. So further looking into the temporal agreement between this PM1, PM2.5 and PM10 concentrations with the lidar derived extinction coefficient, we see that there's a good agreement between this size resolved PM and the lidar extinction coefficients at different times. And this again, we try to make sure we try to make a scatter plot, and PM1, PM2.5 and PM10 are represented in different panels, first on the top panel and middle panel and bottom panels respectively, and they were compared with the scattering coefficients at different wavelengths, 450, 550 and 700 nanometers derived from nephelometer. And this clearly showed that the back scattering coefficients were mainly influenced by the fine mode PM1 and PM2.5 concentrations, while it has a lower correlation with PM10. And in all these cases, we can see clearly that there is a linearity in the relationship. Now, till now we were looking at individual relationships with some of the measurement variables. So, but in order to establish a link between the particulate mass and the lidar signal and others, it's actually a multivariate data analysis problem. And there exist a number of relations between lidar signal, PM, and other retrieved parameters from collocated measurements, and to identify the parameter that has actually maximum influence on the mass extinction efficiency is something that is an important aspect. And so in that perspective, we try to use a principal component analysis. And this principal component analysis actually transforms the correlated variables into smaller number of variables. And as a result, it reduces the dimensionality of the data sets so that it can allow us to identify the trends, patterns, or outliers in the data far more easily. So with this, to establish a relationship, we can always formulate a relation like particulate mass is a function of Lidar extinction coefficient, relative humidity, PM1, PM2.5, PM10, and so on other parameters. So preliminary analysis of our performing, when we performed the principal component analysis, we were considering around 21 variables, and we see that we have assigned each variable a serial number, and we see that the correlation coefficient with respect to the Lidar extinction was obtained different for different variables that we have considered. And Lidar extinction has good correlation, like around greater than 0.7 with wavelength dependent scattering and extinction coefficients, and PM1, PM2.5, and relative humidity. So the redundancy in the data was clearly observed, and cumulative variance of eigenvalues of correlation matrix indicated that many relationships exist between the variables. So moving further, based on this, using the eigenvectors corresponding to the smallest eigenvalue as coefficients of the respective variables, we predict that Lidar extinction coefficient as given by this relation, where AI actually represents the ith eigenvector and xi represents the time series of ith variable, and alpha predicted is the extinction coefficient predicted. So as you see here in the below figure, as a function of time, you can see that both the derived extinction coefficient and the predicted extinction coefficients go 1 in 1, and you can see on the right side that they have a correlation of around 0.77 with a linear relationship. Of course, there were some outliers also, but we see that for 95% of confidence interval, they are having a slope of 0.99.
Sir, sorry for interruption, sir.
Yeah.
We have 5 more minutes, sir.
This is my last slide. Yeah. Okay. So with this, the way forward is that the Lidar extinction can be represented as a linear combination of all other variable parameters, and further work needs to be taken up to reduce the number of variables by identifying the significant ones. And real-time and dynamic mapping of particulate pollution using quantitative indicators in the vicinity of intense sources is still an aspect of research, with ample scope to examine the multivariate regression and machine learning techniques. So with this, I conclude my talk. If there are any questions, please. Thank you.
Thank you, Madhavan, sir, for your clear-cut explanation and stick on to the time also. If you have any questions, please let me ask. Okay, if there is no questions, so once again, thank you to Dr. Madhavan, sir, for your illustrative explanation of the presentation. Thank you.
Yeah.